This video covers section 2.3, sets. Like the concepts of point and line in Euclidean geometry, or the concepts of true or false in logic, the terms set and element are not formally defined in mathematics. Suppose we try to define a set. A dictionary might define a set to be a collection of objects. But then what's a collection? According to the dictionary, this is a group of objects. What's a group? Again, according to the dictionary, an aggregate of objects. After a while, you see that we're just using different words to describe what we mean, but we're really not defining it. While we cannot give a formal definition of a set, we do use the following informal definition. So a set is a well-defined collection of objects. The objects are called the elements of the set. We'll describe what the term well-defined means a little later. We use the notation shown to indicate that X is an element of the set S, and the notation shown to denote that X is not an element of S. We typically use uppercase letters such as A, B, or S to denote sets, and lowercase letters such as A, B, X, or Y to denote elements or possible elements of sets. There are two general methods for specifying sets: the list method and the rule method. Depending upon the specific set, one method may be easier or more convenient to use than the other. In many cases, we must use one method over the other. Using the list method, we specify a set by explicitly listing its elements, separated by commas, enclosed in braces. For instance, the notation shown, A is equal to 1, 2, 3, enclosed in braces, specifies a set containing three elements, 1, 2, and 3. A set is completely determined by its elements. This means that the order in which the elements are listed does not change the set. Also, listing an element more than once does not change the set. Therefore, the following notations all specify the same set: ABC enclosed in braces, BCA enclosed in braces, AACBBB all enclosed in braces. Since listing an element more than once does not change the set, we should list elements only once. The rule method describes a set by specifying one or more rules or properties which the elements must satisfy in order to belong to the set. The set is written using set builder notation, which has the form shown, where D is the domain that the elements of the set are taken from, and P of X is a propositional function specifying the properties that elements of the set must satisfy. The vertical line in this notation is read such that, so the notation is read the set of all X in D such that P of X is true. An element in the domain D belongs to S provided that the propositional function P of X is true for that element. Let's look at some examples now. So the following set is specified using the rule method. A is the set, X is an integer such that -1 is less than or equal to X is less than 5. We want to identify the domain of X, the rule, and write the set using the list method. The domain in this example is a set of integers Z, and the rule is the propositional function -1 less than or equal to X is less than 5, which we can denote by P of X. Using the list method, we can write this set as A is the set containing -1, 0, 1, 2, 3, and 4. These are the integers between -1 and 5, including -1 but not 5. Next we have the set B is the set X is a real number such that X squared minus 2X plus 1 equals 0. Again, we want to identify the domain of X, the rule, and write the set using the list method. For this set, the domain is the set of real numbers, R, and the rule is the propositional function X squared minus 2X plus 1 equals 0, which we can denote by Q of X. Since there is only one real number, namely 1, for which the propositional function x squared minus 2x plus 1 equals 0 is true, then we can write the set using the list method as B is the set containing the single element 1. And next we have the set C is x is a US state such that x begins with the letter M. For this set, the domain is the set of all 50 US states, and the rule is the propositional function r of x begins with the letter M. Using the list method, we can write this set as, well, this is a set containing all the US states beginning with the letter M, which are Maine, Maryland, Massachusetts, Michigan, Minnesota, Mississippi, Missouri, and Montana. In our informal definition, we required a set to be a well-defined collection of objects. This means that for a given set, we must be able to determine whether or not a given object belongs to the set. This is not usually an issue with the list method, since we have explicitly listed the elements of the set. For the rule method, however, we must be able to determine whether or not a given element satisfies the rule P of x. For instance, a description like S is the set x is a US state such that minus 1 less than or equal to x less than 5 is not valid, since substituting a value of x from the domain, the set of US states, does not result in a definite truth value for the propositional function -1 less than or equal to x less than 5. We also sometimes specify sets using a hybrid of the list and rule methods. The notation shown, A is the set containing 1, 2, 3, ... up to 100, can be used to describe the set consisting of all integers between 1 and 100. The symbol with the 3 dots, called an ellipsis, indicates a pattern for the elements of the set and implicitly defines a rule which the elements of the set must satisfy. This notation can also be used for infinite sets, such as B is the set containing 1, 2, 3, ... With this particular notation, we must again be concerned with whether our description is well defined or not, meaning we must include enough elements so that there is no chance of misinterpretation of the elements of the set. For instance, a description like C is the set containing 3, 5, 7, ... out of context could be interpreted to mean the set of all odd integers greater than 1, in which case C is the set containing 3, 5, 7, 9, 11, 13, and so on. Or perhaps the set of odd primes, in which case C is the set containing 3, 5, 7, 11, 13, 17, and so on. Or possibly some other set. Certain sets of numbers occur often enough to warrant special notation, and we've already seen some of these. So n denotes the set of natural numbers or positive integers. Z denotes the set of all integers, positive, negative, or 0. Q denotes the set of rational numbers or quotients of integers, and we can write this using our set builder notation as shown. Q is the set of all fractions a over b such that a and b are both integers and b is not equal to 0. And finally, R denotes the set of real numbers. For our next example, we'll define an integer n is even, provided that n is equal to 2k for some integer k. We want to write the set of even integers using set builder notation. We can use z for the domain. An element n in z then belongs to the set of even integers, provided that it satisfies the rule P of n is there exists a k in z such that n is equal to 2k. We can then write the set of even integers as shown. It's a set of n in z such that P of n is true. Next, we want to write the set of perfect squares between 1 and 100 inclusive using set builder notation. So first we need to define what we mean by a perfect square. So an integer n is a perfect square provided that n is equal to k squared for some k in n. So n is the square of a natural number n, k, sorry. We can use n for the domain. An element n in n belongs to the set of perfect squares between 1 and 100, provided that it satisfies the rule shown. So Q of n is, there exists a k in n such that n is equal to k squared, and 1 is less than or equal to n is less than or equal to 100. The set can then be written as the set of n in n such that Q of n holds. And finally, we want to write the set of points x, y in the Cartesian plane that lie on the circle x squared plus y squared equals 1 using set builder notation. We can let r squared denote the set of all points x, y in the Cartesian plane. Then a point x, y in r squared belongs to the set provided that it satisfies the rule r of x, y is x squared plus y squared equals 1. The set can then be written as the set x, y, and r squared such that x squared plus y squared equals 1.